UPAC is the International Union of Pure and Applied Chemistry. It is an international scientific organization not affiliated with. The UPAC strives to advance chemistry, in part by setting global standards for names, symbols, and units. Nearly 1,200 chemists are involved in UPAC projects. 8 standing committees oversee the union's work in chemistry. The UPAC was formed in 1990 by scientists and academicians who recognized a need for standardizations in chemistry. The predecessor of the UPAC, the International Association of Chemical Societies, IACS, met in Paris in 1911 to propose issues that needed to be addressed. From the beginning, the organization has sought international cooperation between chemists. In addition to setting guidelines, the UPAC sometimes helped to resolve disputes. An example is the decision to use the name sulfur with F instead of both sulfur and sulfur with PH. An hydrocarbon is an organic compound made of nothing more than carbon and hydrogens. It is possible for double or triple bonds to form between carbon atoms and even for structures such as rings to form. They are found in many places, including crude oil and natural gas. The classification for hydrocarbons defined by the UPAC nomenclature for organic chemistry are as follows. Saturated hydrocarbons, also named alkanes, are the simplest of the hydrocarbon species. They are composed entirely of single bonds and are saturated with hydrogen. The general formula for saturated hydrocarbons is CnH2n plus 2, assuming non-cyclic structures. Saturated hydrocarbons are the basis of petroleum fuels and are found as either linear or branch species. Substitution reaction is their characteristic property, like chlorination reaction to form chloroform. Hydrocarbons with the same molecular formula but different structural formula are called structural isomers. The other classification is unsaturated hydrocarbons. They have one or more double or triple bonds between a carbon atoms. Those with double bonds are called alkanes. Those with one double bond have the formula CnH2n. Those containing triple bonds are called alkenes and their formula is CnH2n minus 2. Cycloalkanes are hydrocarbons containing one or more carbon rings to which hydrogen atoms are attached. The general formula for a saturated hydrocarbon containing one ring is CnH2n. Aromatic hydrocarbons, also known as RNs, are hydrocarbons that have at least one aromatic ring. Hydrocarbon derivatives are compounds made up of carbon atoms and at least one other atom that is not hydrogen. Some examples are halogenated hydrocarbons. They are hydrocarbon derivatives in which one or more halogen atoms have replaced hydrogen atoms. Such compounds are named using the rules that apply to branch chemistry, with halogen substituents being treated the same way as alkyl groups. Alcohols and phenols are hydrocarbon derivatives that contain an hydroxyl group attached to a saturated carbon atom. The general formula for an alcohol is ROH. Phenols have the general formula AROH, where AR represents an aryl group derived from an aromatic compound. Thiols and disulfides. Thiols are the sulfur analogs of alcohols. They have the general formula RSH. The SH group is called the sulfihydryl group. Oxidation of thiols form disulfides, which have the general formula RSSR. The most distinctive physical property of thiols is their full odor. Amines. An amines is an organic derivative of ammonia, NH3, in which one or more hydrogen atoms of the nitrogen atom of ammonia have been replaced by an alkyl, a cycloalkyl, or an aryl group. Amines can be classified as primary, secondary, or tertiary, depending on the number of hydrogen atoms of NH3 that have replaced by hydrocarbon groups. In this table, we can see some common functional groups, their general formula, and their prefix or suffix.
But we need to know what are alkanes. Alkanes are hydrocarbons which contain only single bonds. They are called saturated hydrocarbons because there is an hydrogen in every possible location. This gives them a general formula like this one, showed here. CnH2n plus 2. How to name them according to UPAC rules? The first step we need to do is to count the number of carbons in the chain. So let's suppose we have this compound. We have 1, 2, 3, 4, 5, 6 carbons. Remember that each point of the chain is a carbon. So according to this table, we have all the prefixes according to the number of carbons we have in our chain. We have 6 carbons, so our prefix is gonna be hex. And since we are talking about an alkane, our suffix is gonna be ane. The result, hexane. Let's do another example. We have this compound, and we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. We look at the table and we notice that since we have number of carbons 8, our prefix is gonna be oct. So it's gonna be octane. Now, if the alkanes branch, we have to identify first the longest chain. Let's suppose we have this 1, 2, 3, 4, 5 carbons in this formula. 1, 2, 3, 4, 5 carbons. This is our longest chain. But if we look here, we have another chain. But since this is the longest, we're gonna take that. So we have a substituent. We need to count. The longest chain has 5 carbons. This one. So our substituent, we have to locate it. We have to count from right to left or left to right in order to locate it in the lowest number. For example, since we have here the same number, we need to count. From right to left is 1, 2, 3, 4, 5. The substituent is in carbon number 4. But if we count from left to right, we have 1, 2 carbons in the carbon number 2. So since it is in our carbon number 2, it's gonna be 2, and our substituent is an alkyl group, and it has just 1 carbon, so it's 2-methyl. Meth is the prefix for 1 carbon. This is 2-methyl pentane. Why pentane? Because our longest chain has 5 carbons, so the prefix for 5 carbons is pen. 2-methylpentane.
Alkenes contain carbon-carbon double bonds and are unsaturated hydrocarbons with molecular formula CnH2n. Alkenes are named with a prefix that indicates the number of carbons contained in the hydrocarbon, and the suffix "-in" that tells us we have double bonds in it. For example, if we have a hydrocarbon with 2 carbons and double bonds in it, how will we call it? First, we know that 2 carbons are represented with the prefix "-eth", and then we just have to add the suffix "-in" to this word to form ethene, the name of the compound. Thus, if we have a hydrocarbon having 3 carbon atoms, we will have propene, that comes from prop, which indicates 3, and "-in", that says that we have double bonds. In this way, a hydrocarbon with 7 carbon atoms and double bonds in it will be called heptene. The simplest alkene, ethene, has 2 carbon atoms and a molecular formula of C2H4. The structural formula for ethene is displayed on the screen. In longer alkene chains, the additional carbon atoms are attached to each other by single covalent bonds. Each carbon atom is also attached to sufficient hydrogen atoms to produce a total of 4 single covalent bonds about itself. In chains with 4 or more carbon atoms, the double bond can be located in different positions, leading to the formation of structural isomers. For example, the alkene of molecular formula C4H8 has 2 isomers. You can see it on the screen. Stereoisomers. In addition to structural isomers, alkenes also form stereoisomers. Because rotation around a multiple bond is restricted, groups attached to the double-bonded carbon atoms always remain in the same relative positions. These locked positions allow chemists to identify various isomers from the substituent locations. For example, one structural isomer of C5H10 has the following stereoisomers displayed on the screen. The isomer on the left, in which the two substituents, the methyl and ethyl groups, are on the same side of the double bond, is called the cis isomer, while the isomer on the right, with two non-hydrogen substituents on opposite sides of the double bond, is called the trans isomer. If more than two substituents are attached to the carbon atoms of a double bond, the cis and trans system cannot be used. With such chemicals, EZ notation is used. In the EZ system, the molecule is first bisected vertically through the double bond. Second, the two atoms or groups on each carbon atom are ranked by atomic weight. The higher atomic weight is assigned priority. For example, in the figure displayed on the screen, the carbon and chlorine atoms on the left side of the bisecting line are ranked. Chlorine has priority because it is heavier. On the right side, bromine outranks carbon. Third, the positions of the two atoms of higher rank are determined. If the two atoms are in the cis position, the arrangement is C. If the atoms or groups are in the trans position, the arrangement is E. The name of the chemical in figure displayed on the screen is E2-bromo-3-chloro-2-butene.
Alkynes are a type of hydrocarbon, which are molecules of hydrogen and carbon, which contain a triple bond. And because of this triple bond, it is also called as an unsaturated hydrocarbon.
Like alkanes have the suffix "ane", alkenes use the ending "in". This suffix is used when there's only one alkene in the molecule. To name an alkene in base of its structural formula isn't much difficult. We can follow the next steps to name an alkene in base of the UPAC system. First, we need to find the longest carbon chain that includes both carbons on the triple bond. After numbering the longest chain with the lowest number assigned to the alkene, label each of the substituents and its corresponding carbon, while reading out the name of the molecule. Arrange the substituents in alphabetical order. If there are more than one of the same substituent, use the prefixes D, 3, and tetra for 2, 3, and 4 substituents, respectively. These prefixes are not taken into account in the alphabetical order. Then, number the longest chain starting at the end closest to the triple bond. When the substituents contain a triple bond are called alkenyl. This suffix is used when there's only one alkene in the molecule.
So at the final, in this example, we're going to find that the triple bond is in the number 4, so it's 4-hexane, and the substituent is in the carbon number 2, so it is 2-methyl. And if we put them together, we're going to find that the name of this hydrocarbon is 2-methyl-4-hexane. If we solve this example, we're going to find that we have five carbons, so the name will begin with penta. Then in the carbon number 2 begins one triple bond, and in the carbon number 4 begins the other one. So, or the name of this alkene we're going to be 2,4 pentane, because we conserve the prefix. In this last example, we have 3 carbons and 1 triple bond. We don't have substituents, so we keep the prop because it is 3 carbons, and we allow the prefix that is ane, so it's propane, and it is in the first carbon, so we don't need to put the number. So the name of this hydrocarbon or this alkyne will be propane. Draw a structural formula. It is much easier. Let's suppose that we want to draw the structure of 3-octane. It is said oct, that means that it has 8 carbons. So we draw the 8 carbons, and then say that in the third carbon it has a triple bond. So we draw the triple bond in the third carbon, and we have it. If we have this alkane, first we need to observe that we have pentane, so it will have 5 carbons. So we draw the 5 carbons, and we see that in the first carbon we have the triple bond. After that, in the third carbon we have 2 methyl groups, so there's only 1 carbon per each, so we draw one up and the other down the carbon, and we get it. Finally, if we have propane, we get the prefix or the name prop, that is 3 carbons. We draw the 3 carbons, and like there's no number, that means that it's the number 1 at the beginning. So the triple bond will be in the first carbon. We draw the 2 lines to get the triple bond, and we get it.
Okay, now let's start with the aromatic compounds. Any of a large class of unsaturated chemical compounds characterized by one or more planar rings of atoms joined by covalent bonds of 2 different kinds. The unique stability of these compounds is referred as aromaticity. To name them, follow the next steps. First, all the names turn around the benzene ring. That is one that can identify aromatic compounds. Step number 2. Remember that you get a methyl group, that is CH3, by removing a nitrogen from methane, CH4. And the same applies here. You get a phenyl group, that is C6H5, by removing a hydrogen from a benzene ring, C6H5. Like a methyl or an ethyl group, a phenyl group is always attached to something else. Step number 3. Find the substituents and name each of them with an appropriate group name. Substituents is an synonym of prefix or suffix. Step number 4. List the group alphabetically in front of the longest chain name, that is benzene. Okay, now let's practice these steps with 3 examples. Example number 1. Okay, here appears the benzene ring, but it has something attached. So in fact, what it appears here is a phenyl group. In order to attach something else, you have to remove one of the exciting nitrogen atoms and so automatically make a phenyl group. Okay, now we got the benzene ring, and this is the termination of the name of the formula.
Step number 2. Now we know that it's a phenyl group with something attached else, but it continues being a phenyl group. Step number 3. Find the substance or the names for the atoms that are being attached to it. In this case is a chlorine. So the substituents for it is chloro, and it's the only one that appears. Step number 4. Listen groups alphabetically in front of the longest chain name that is benzene. Benzene plus chloro before that is chlorobenzene. Okay? Now we got the example number 1. Okay, another obvious name. The benzene ring has a methyl group attached. Other alkyl side chains will be named similarly. For example, ethylbenzene. Okay, the simplified formula for this is C6H5CH3. And again, the 4 steps. Step number 1, benzene ring. That is the longest name that will appear in the formula. Okay, now we know that what type of group it's, and it's a methyl group. So, to step number 3, find the substituents for the CH3 that is attached to the benzene ring. In this case it's methyl, and how it's the only one, only will be added to benzene. To example, this one will be a little bit harder. Okay, a variant on this which you may need to know about this is where one of the hydrogens on the CH3 group is replaced by a chlorine atom. Notice something here. There are 2 atoms attached together, but there are no one attached to the benzene ring. Okay, now the first steps. Okay, the main branch is the benzene, so it will be the last name appearing. Okay, we have CH2, that it means that is a methyl group, but it doesn't have, it is just a nitrogen atom because a chlorine atom is added. Step number 2, we define what it is. Step number 3, we got that chlorine and methyl are the substituents for the 2 atoms or the 2 molecules that appear here. So in the step number 4, by adding them alphabetically, it will be chloro, methyl, benzene, and that's the name. Now let's see it from another perspective. We're going to get the structure of the aromatic compound based on its name. Step number 1. Know how the aromatic compound is arranged by its name, like the examples that we said before. Step number 2. By logic, the benzene ring will be applied to it, so let's add it from the beginning. Step number 3. Attach the other part of the compounds based on their names. So to make it easier and more easy to understand it, we are going to use the 3 examples from before, but now it's names to get the structure. Example number 1, chlorobenzene. Okay, now let's follow the steps. Step number 1. Know how the aromatic compound is arranged by its name. Okay, it has 2 names that are fusioned to make it, chloro and benzene. Okay, step number 2. By logic, the benzene ring will be applied, so let's add it. Step number 3. Attach the other parts, in this case chloro, of the compounds based on their name. So if we add chlorine to the benzene ring, we got the structure that we saw in the first example. Example number 2, methylbenzene. Another obvious example, it will be the same steps and it will be the same process. Okay. Step number 1, dividing its parts by its name, methyl and benzene. Adding the benzene to the structural formula, the drawing, and then the other parts, the other names that are forming the name, in this case methyl, CH3, we add it and we obtain the second example by its structure and name. The example number 3, that is the harder in both ways. Chloromethylbenzene. We see that chloromethyl is in brackets. This means that chloro and methyl are attached by one with each other and not random in the ring, they are both together. So again, knowing its parts, chloro, methyl, and benzene, then adding the benzene ring, and for last step we add the other two names that are chloromethyl. They are both together, so they will be appear one near to each other. CH2Cl. And that was the last example for getting the aromatic compounds. Thank you.